Hi, my name is Henry Brill, and this is V5, the flux integrals. All right, so the first step here is to see what the question means. So when they say first octant with upward orientation, that's pretty crucial information because it tells us that all x, y, and z are going to be greater than 0. So yeah, and also it tells us that for in upward, also the upward pointing, the normal vector, which we need to know later, for upward pointing surface is for a function, just for a function g is negative g partial with respect to x, and then y comma 1. All right, so that's what we need to know for this. So we have our function, we have our plane. We know where it is, so yeah, that's the first step. Okay, so for our formula, we have this for surface, the plane S, I'll call it. It's f, our function, dotted with normal. And then we have ds. Yeah. Sorry, wait, that should be a ds. Okay, and then this is the same thing as we have this in our function. It's just rewriting everything we have. It's the same thing as x, comma y, comma g of x, comma y. So that's the same thing as that, because z is equal to this. Z is equal to function x comma y. And then that's the first part, and then we dot, and then our normal vector, which we can use substitution from earlier. We got the x component, y component, and then just 1. And then we got dA. All right. Cool. So now we can actually substitute in for our function. Or yeah, we can do that. Or actually, no. I think it'd be easier to solve for the normal vector first. So, all right, we have our function for our plane, which we're going to arrange in terms of z. So we have z equals 2 minus x minus y, just by rearranging what side x and y are on. And this is the same thing as g x comma y equals that. Okay, cool. So now we have this established. So let's see. We're going to find the unit normal vector. So that is, we have to take the derivative with respect to x, which is just negative 1. You can see right here, because this is the only x term, coefficient is negative 1. So here I'm going to do n. We have negative 1. And now for the y, which is derivative with respect to y, only y term is this, the coefficient, once again, negative 1. So negative 1 again. And then we have 1 from our formula. Just 1. So that's the first part. Now we have to plug into this. So f, and this, we can see right here. So we have xy, z, and x plus y. but we want the whole thing in terms of x and y. So x, y, comma, z, x plus y. And this could just be rearranged as, since like vector, we got this, just rearranged as x, y, the same thing, just different format. It makes it easier for the next part. And then, before we want to make this substitution in for z, which we have to get it in terms of x and y, 2 minus x minus y. So we're going to put this here for z. And then last x plus y. Now we have that. All right, cool. So, I just realized. So, this, since it's the opposite of the partial gx, something was wrong, and the partial gy, and since just the partials themselves are negative, we have to do the opposite of it. So this will be positive and this will be positive. Just a glance and caught that. So these are both positive because negative times negative is positive. All right, so now we have to solve for our integral here. Or plug in, not solve yet. So now we could rearrange the f dot n. This is just x, y, 2 minus x minus y, x plus y, and then just dot 1, 1, 1. Our normal. So now we just add all of these, and all right, so that is that. Cool. Awesome. Now we have that. Let's see. We got this here, this there. Yep. All right, so then the next step, I forgot to include, this is not just normal, it's n ds equals this. That's my fault. And yeah, now we get to simplify this. So this all just cancels out. We have xy plus 2. So f dot n ds, and then this whole thing, we have to include the dA. Equals just x, y plus 2 and then for this we have to include then the double integral over s. So now to find the actual bounds. So x just greater than 0 less than 2. So x will go from, because it's, bounded by this plane. We'll use x for this. We'll go from 0 to 2. Because it's in, first octant, so it's greater than 0. So we're gonna go 0. And then y is a little bit more complicated. We have to, so we have this. We could use this formula so we know, here, we'll go back up here. So we know y is greater than 0. Y is greater than 0. Or sorry, we know z is greater than 0 because it's in the first octant. So we could plug this in for z. And we have 2 minus x minus y greater than 0. Add y to both sides, and we get 2 minus x greater than or equal to 0. Or sorry, this would be y greater than or equal to y, and then we know y is greater than 0 because it's in the first octant. So that it goes from 0 to 2 minus x. That's our bounds for this. And boom. All right, so now we could set up our actual integral. Since we have a function, we want this to be the inner, so we're gonna put x on the outside. So 2, 0. Minus x 0. Then our function was just xy. And then dy dx, because we want y first. Now I can put this in Wolfram alpha. And see what this gives us. And this gives us our answer. And yeah, that gives us our answer, 14 over 3. Yeah, that's it. Thank you.